Hi everyone. In this video, I want to discuss concentration because there are many ways that scientists can express concentration. Well, not just even scientists. Right now I have an example of vinegar that I got from the grocery store, and it tells me that it is 5% acidity. So if we could determine whether it's 5% by volume or by mass, we can convert to other concentration units such as molarity and molality. I'll try to remember to do that example in this video as well. Okay, concentrations. Oops, get this cord out of the way. The example that I used in a previous video is that of tea. And we're putting sugar in that tea. It's a spoon, we have a pile of sugar, and it goes in, and we dissolve some sugar. When you think of dissolving, think of solvation or solvating, and the water molecules surrounding that sugar. Well, sugar has a molecular formula of C12H22O11, and I kind of messed up the general rule or the rule of thumb. Let me try it again. If you have a ratio of, we call these heteroatoms, atoms that are not carbon or hydrogen, of O, N, F, Cl, Br. These are all pretty electronegative. Of one or more to 4 carbons. So for instance, if you have an oxygen to carbon ratio of 1 to 4, you can assume that that molecule is polar and it will be water soluble. But look at our ratio here. Our ratio is 11 to 12. 11 oxygens to 12 carbons. We're going to consider this molecule polar and therefore water soluble. The name for table sugar is sucrose. Let's take a look at the structure of sucrose real quick. Okay, and you can see that actually they don't write out the carbon atoms for the ones that are intersecting here. Every time you see an angle, you could assume that that is a carbon atom. And you notice that, yeah, you have almost a 1-to-1 ratio of oxygen to carbon. When we take a look at the solubility, it says sucrose has the greatest solubility of the disaccharide sugars. It's 204 grams for every 100 cubic centimeters. So that's interesting that they would express a concentration in those units. Let me write that down. 204 grams per 100 cubic centimeters of water. Let's take a look at that concentration on paper. Okay, it's right there. So they chose to express the amount of sugar in grams and the amount of water in cubic centimeters. We know that 1 cubic centimeter equals 1 milliliter for any substance because both of these are volumes. Okay. So let me go over the other ways to give concentration. Oh, by the way, I got an email. This is not just tea. We're in the South. This is called sweet tea. My apologies if you were offended. First type of concentration units, molarity. We'll call this number 1, molarity. We need amounts of solute and amounts of solvent. But before we get to these different types of concentration units, let me specify, because not only do we have the amount of solute that we would need to know, we may want to know the amount of solvent, but some of these units actually depend on the amount of solution, which is different. Solution is solvent and the solute together. And that's going to be the case for molarity. We don't want the liters of solvent in the solution. We want the liters of solution, the solute plus the solvent. And it's not always going to be obvious. For instance, when you dissolve ethanol in water, a cup of ethanol plus a cup of water would not equal 2 cups of solution. You would have to do this experimentally because one would dissolve in the other, so it wouldn't be exactly or up to 2 cups. Molarity. So molarity, as an example, you could see it as a big M. So 1.45 big M of sodium chloride, NaCl. And then you know that when you dissolve that, sodium chloride will be aqueous. Not only does it dissolve, but the ions are actually solvated, so it actually dissociates, break up into its ions. That is the same as saying 1.45, and it's called molar. Okay? It's a molarity. A molarity is just a fancy word to say concentration, but it's concentration in molar. That is a unit. So what is a molar? This is the same as 1.45 moles of NaCl per liter. So this is where you'll see the distinction. It's not liter of water, it's liter of solution, water plus the solid sodium chloride that got dissolved. That's very, very important. Okay. So when you're doing problems like this, they'll tell you actually most of the time whether you have the amount, like for instance 4 liters, whether that's the amount of solvent, but most likely they'll say it's the amount of solution. Okay, so again, you have a distinction between solvent and solution. They may be close, right? They may be close, but they're not technically exact. So just a hint, if you are going to use a molarity in dimensional analysis, automatically write moles over liters. So let's say we have 7.2 liters of what? Of solution. And I want to figure out how many moles of sodium chloride I have. Well, I have a molarity, and the molarity is the conversion. 1.45 moles of NaCl over what? 1 liter of solution. Because the molarity I'm using is 1.5 moles per liter, 1.45 moles per liter. And you notice that the liters cancel out and the solution cancels out. Technically, this is, well, solution of NaCl, so maybe we don't have to write that NaCl over there. Ultimately, you get moles of NaCl. 7.2 times 1.45, you get 10.44 moles of NaCl. And you know what you can go from there, where you can go. You've seen problems before. You could get grams, right? What could you also do? You could dissolve this in a different amount of water to get a different concentration. So you could get different molarities, depending on how much you dissolve or dilute. Not in this video, but In later videos, when we do problems, we'll do dilution problems. Make this maybe 0.25 molar instead of 1.5 molar. That is molarity, moles per liter. And you could abbreviate moles per liter eventually with big M. But again, dimensional analysis, you want to see numerator and denominator units. Next, molality. I made this small, lowercase, because while molarity unit symbol is big M, molality is little m. And we could still use sodium chloride, but now we're going to express it as a molality. Okay, so language becomes very important because we have molarity, we have molality. Molarity is measured in molar, molality is measured in molal. So if I have 1.45 little m of NaCl, that equals 1.45 is called molal. Molarity by far is the more common. Molality we'll see in a couple of equations later in this unit when we talk about colligative properties, boiling point, melting point. The concentration of a solution can alter those properties. Well, what the heck is a molal? This is equal to 1.45. It's still moles on top over kilograms. Now we're using a mass. Kilograms of what? Kilograms of, I gotta cheat. Is it solvent or is it solution? And for molality, it is just the solvent. Oof. Okay? Just the water in most cases. I gotta remember that. So it's different. Not only is the type of unit different, we went from liters to kilograms, but just as important, we went from liters of solution to kilograms of solvent. Okay. Again, not in this video, in definitely a future Unit 4 video, molality is important with colligative properties. The equations use molal. Colligative, most likely the next video. Colligative properties, oh boy, colligative properties, equations. Number 3. This is fairly self-explanatory, I hope, but you may see something that looks like that. Percent V to V. This is percent volume to volume. And I'm already sweating it because do I need the volume of the solvent or do I need the volume of the solution? Let us say, again, 1.45 percent V to V of, oh, sodium chloride is a solid, so I don't want to use that per se. Let me use a liquid. Let's say acetone. Acetone's a liquid in water. Volume to volume. So this is equal to the volume of acetone over, I'm stalling, the volume of, is it water or is it the addition of water and acetone? Volume of solution. And how am I going to remember that? This is the V total. So if you have 5 milliliters of acetone and 100 milliliters of water here, then you could assume it's 105, the total volume solution, if they tell you that they are additive. And actually they may not be. 5 milliliters of acetone plus 100 milliliters of water, you would want to verify experimentally whether that is a 105 total, or is acetone kind of fitting in between the water and it's almost no added volume. But anyway, that is volume to volume and it's a percentage. You know what? I shouldn't have sweated this. When you have a percent, that equals part, so that's the acetone, the solute, over whole. That's the summation, the total volume, water and acetone, times 100. I gotta remember that. Percent is part over whole. Part over whole. Because what if it was percent mass to mass? That's different. We're gonna use maybe grams. So for this volume, maybe it can be milliliters or liters. Just make sure they are consistent with each other. You measure in the same units. Percent mass to mass. Just circle those two. Percent mass to mass. 1.45% mass to mass. Now that I'm confident that it's part over whole, this is the same as maybe grams of acetone. Now, usually mass is additive. You put it on the balance and you have 100 grams of water. If you add 5 grams of acetone, the total mass should be 105 grams. That is relatively accurate. You could just add up the two. Grams of not water, but grams of solution. So to specify, that is acetone plus water. By the way, is acetone really soluble in water? Let me just put here 100% before I forget. Is acetone soluble in water? This was in a previous video showing you ways to determine water solubility. Acetone looks like this. It almost looks like formaldehyde that I mentioned in the video about solubility. You have that. Look at the bond dipoles. Definitely you have that. And a carbon-oxygen bond, double bond, is a pretty large dipole. This molecule has a net polar molecular dipole, so the molecule is polar, therefore water soluble. The carbon to oxygen ratio, or the oxygen to carbon ratio, is 1 oxygen to 3 carbons. So it's working. That's better than a 1 to 4 ratio, right? Okay. Let's go to the vinegar example that I mentioned at the beginning of the video. Vinegar is acetic acid in water, and they say 5%. Because it's acetic acid, and I know that's a liquid, I'm going to assume that they mean 5% volume to volume. Okay. What possible problem would you be expected to know how to do? Convert 5% volume to volume to molarity. Most chemists use molarity when they run a reaction. How much reagent is dissolved in some solvent? Example, convert 5.0%, and we're going to assume it's volume to volume. But on an exam problem, you'll be told vinegar. What is that? Oh, sorry. Convert it to molarity. Now I could have asked you to convert it to molality or even percent gram to gram. We could do that because we know the weight of water if we know the volume, right? 1 milliliter of water equals 1 gram. But anyway, this is the instructions. Vinegar is acetic acid, so that's the solute in water. So here we have a solute, and it's a liquid, and this is water, obviously a solvent. Liquid. Okay. Acetic acid. We should give you that. Acetic acid. Oh my goodness. Volume. We need molarity. So we need moles. To get moles, we need grams. So yes, we need the density and the molar mass of acetic acid. And if I'm writing the problem, I'll probably give it to people. So acetic acid. Let's do density first. Okay. Do you have any other information? Acetic acid is... Okay, we got molar mass. So acetic acid, the density equals... Do I need density? We'll see. Centimeter cubed is the same as milliliters. So 1.05 grams per milliliter. And what the mass, we'll call it mm, the molar mass, equals 60.05 grams per mole. So we don't need the molecular formula because they already give us the molar mass. But the molecular formula, just in case you're curious, C, it comes from acetate, the acetate ion. So the acetate ion, C2, H3O2, but because it's an acid, pick up another hydrogen. Okay, we have all the information we need. That right there. So if it's 5%, we know that we have 5 milliliters of acetic acid over total volume, 100 milliliters of solution. That's water and acetic acid. Isn't that 5%? 5 divided by 100 times 100% is 5%. Uh-oh, now I'm stalling. Well, I need for molarity not only the moles, but also the liter. Thank goodness this is liters of solution. I don't have to break it up and figure out how many liters of solvent I have. It's not of solvent, it's of solution. That's good about molarity. So I have solution right here. I don't need to change that, but I need to change the units. Let me show you how I would do this using dimensional analysis. Milliliters. Well, let's change it to grams. 1.05 grams of acetic acid per milliliter. That's coming from the density. Is this thing too bright? Okay. And I keep acetic acid. So that's gone. But I need moles. I need moles. So we take the inverse. We have 1 mole of acetic acid for every 60.05 grams. And are we done? Not yet. We get rid of the grams. We have milliliters, but molarity is liters. Therefore, we multiply 1 milliliter is to 1 times 10 to the minus 3 liters. I know most are going to say 1,000 milliliters equals 1 liter. It's the same ratio, so it would work as well. But what do I accomplish in this case? The milliliters cancel out. Look at what is left over. Acetic acid, moles per liter. That's what we need. So you could do this all in one row of dimensional analysis. I press enter after each operation. 5 divided by 100 equals times 1.05 equals divided by 60.05 equals divided by 1 times 10 to the minus 3. I don't need parentheses if I use the E button. Equals. Good. 0, it's a reasonable number. 0.87, we'll keep it at 2 sig figs, molar acetic acid in H2O. That is your molarity. On your own, convert that into molality. That is a challenge because we got to figure out now for molality kilograms of solvent. Kilograms of solvent. Super challenging because we got to subtract out the acetic acid that we have. Now, before I end this video, what did I do here? I assumed, or not assume is the wrong word, I pretended that I had 100 milliliters of solution. If you pretend that you had 200 milliliters, it will still work out because this number will scale up as well. But I made it easy. I don't know how to spell pretend. Pretend you have 100 milliliters of solution. But you can pretend any amount because it's a percentage that we're working off of. Okay. Try your textbook problems and maybe future videos, especially when I do some online homework problems and test problems for this unit, we'll do more conversions of concentrations.